Hello everyone. In this video we're going to be simplifying a numerical expression. We have 2 to the power 54 plus 1 divided by 2 to the power 27 plus 2 to the power 14 plus 1. Now, when you look at the numerical values of these numbers, you're going to be amazed because they're very, very large. For example, what is 2 to the power 54 plus 1? It looks like this. We're going to write it with using a lot of digits. So I'm going to go and write it down first, and then I'm going to read it. So 2 to the power 54 plus 1 is equal to 18 quadrillion, 14 trillion, 398 billion, 509 481,985. This is a gigantic number. What about the bottom number? Let's go ahead and take a look at that too. That number is going to be obviously much smaller, and it's going to look like this. And obviously we can read it as 134,234,113. Awesome. So you can go ahead and divide this number, the top number, by the bottom and expect to get an answer. Let me tell you something. The answer is going to be an integer. So we're going to try to find it by using algebra. First of all, I want you to notice one thing. The greatest common divisor of 14, 27, and 54 is 1. There's nothing that divides all of them except for 1. So we're going to think about this. All right, so I kind of want to compare 2 to the power 54 with 2 to the power 27. And I just noticed that 2 to the power 54, I didn't just know about you. You probably already know this is fairly simple. 2 to the power 54 is 2 to the power 27 squared, because 2 times 27 is 54. But what about 2 to the power 14? What are we going to do about it, right? So we need a smarter approach. So here's what I'm thinking. 2 to the power 14 is 2 times 2 to the power 13. And then 2 to the power 27 is 2 times 2 to the power 26, which can be written as 2 times 2 to the power 13 squared. And then 2 to the power 54, since it's 2 to the power 27 squared, we can write it as 2 to the power 27 squared. And since 2 to the power 27 equals this, we can just go ahead and square both factors and write it as 2 to the second multiplied by 2 to the power 13 to the fourth power. Okay, great. So that kind of gives us some idea about how to proceed. And we're going to set 2 to the power 13, our magical number, equal to x. It's kind of like a very squiggly equal sign. Okay, we're going to set this equal to x, and this implies the following. We have 2 to the power 54 plus 1 divided by 2 to the 27 plus 2 to the 14 plus 1. So 2 to the power 54 is just going to be x to the fourth multiplied by 2 squared, which is 4. So we can write it as 4x to the fourth plus 1. And 2 to the 27th is 2 to the 13 squared times 2. So we can write it as 2x squared. And 2 to the 14 is just 2 times 2 to the 13. So we can write it as 2x and then plus 1. Awesome. So what is so good about this? So the million-dollar question is, can this be simplified? And the answer is, of course, it can be. Here's how we can simplify it. So I'm going to go ahead and show you how we can simplify this expression, like the top, and then use the bottom, and then we're going to name it. Okay? We're going to give it a name. But first I got to show you what it looks like. So I'm going to start off with 4x to the fourth plus 1. You can also consider this as a sum of 2 fourth powers, but 4 is not a fourth power. So, you know, even if that 4 is a 16, this is going to work. But sometimes we just have x to the fourth plus 1. So we can still factor it. Anyways, so 4x to the fourth plus 1 can be written as follows. I can just complete the square. So like add 4x squared and subtract it, right? And that is going to be balanced. But notice that this is going to be a perfect square, and this is a perfect square. Everything is perfect. Okay, great. So this equals 2x squared plus 1 quantity squared, and this is 2x quantity squared. Awesome. This reminds you what? Difference of two squares. Awesome. So from here, 4x to the fourth plus 1 can be factored. Again, I'm going to name this for you a little bit, tell you what it's all about. So conclusion, this can be written as 2x squared plus 2x plus 1. I'm just going to put my polynomial factors in standard form because they look better, and write it like this. Great. And guess what this is called? It's called, well, this has been discovered by Sophie Germain. Who is Sophie Germain? Sophie Germain is a French mathematician, but she is also a physicist and a philosopher. You can definitely search up and find a lot of good information about her. Awesome. So using Sophie Germain identity, we can do the following. Our expression is 4x to the 4th plus 1 divided by 2x squared plus 2x plus 1. But the numerator can be factored, just like this, right? So this gives us 2x squared plus 2x plus 1 times 2x squared minus 2x plus 1. And all of that is divided by 2x squared plus 2x plus 1. And this is awesome because one of the factors will cancel out. Beautiful. So we're going to go ahead and cancel these out, and we're going to end up with 2x squared minus 2x plus 1. But that's not the ultimate goal, because x is something we used, right? X is 2 to the power 13. Let's go ahead and back substitute. So our expression becomes 2 times x squared, which is 2 to the power 13 squared, minus 2 times 2 to the 13 plus 1. And then this becomes 2 to the power 27 minus 2 to the power 14 plus 1. And remember, the original expression was 2 to the power 54 plus 1 divided by 2 to the power 27 plus 2 to the power 14 plus 1. So if you write it here again, you kind of see a better association with the answer and the bottom, because those are the two things that multiply together to create the difference of two squares. Awesome. So this is a really cool rule, and you can kind of put it together. But let's go ahead and evaluate this. Obviously, at the beginning, remember, we had like gigantic numbers, right? It was like 18 gazillion. Was it gazillion? What was it? Okay, I think it was quadrillion. Anyways, you get the idea. So 18 quadrillion something divided by 134 million. So those are giant numbers. I don't think you want to divide them, right? Unless you use a calculator. Wolfram Alpha is going to do it for you. It's going to do it for you too, like this one. But that's not the point. Anyways, I talk too much. So this is our expression. What am I going to do with it? I'm going to tell you what the numerical answer is. All right? So this equals 134,201,345. So if you remember, the numerator of the expression that we were trying to evaluate, it was also in the 134 million. So these numbers are pretty close, right? Compared to the top, they're like really close. So yes, we kind of get like 134 million twice. They're multiplied together to, make up the gigantic number, which is the numerator. Awesome. We could also use long division with the polynomials, obviously. If you didn't know Sophie Germain, you could go ahead and divide and you would get the same answer. No big deal, you can do it, but I'm going to give you something else. And that is the prime factorization of this number, which I kind of find interesting, because it can be written as 5 times 109 times 246,244, 41 I mean. Okay, so it is the product of 3 prime numbers. Isn't that interesting? I find it interesting. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.